Hello, Bill Power here, speaking to you from the Archean Craton in Western Australia. Very old rock, very old weathering profile behind me. We're out here looking for gold, maybe battery minerals. I'll tell you a little bit today about, well, why did we end up writing a paper about the North Sea and what was the interest?
Hi, folks. We're back in the office now. Bill's out of the desert, and we're just thinking about the paper that's going to come through in the Geological Society. Um, and I guess part of the reason for recording this is to get you an idea about our thought processes, where we're coming from. So it started out earlier this year in the run up to COVID. Bill and I just published a paper on juxtaposition analysis and shale gouge ratio and trying to understand the uncertainties on there. And we'd been through the process, we'd been re- looking for case studies and found it hard to find case studies. So it was great with the publication of our paper in the special publication comes through a case study from the guys at Badley's. So that's where we launched out into having a look and seeing how we can do it. Now, this data set is a classic data set. It's been used in Graham Yielding's 1997 paper. So when we got the field in the paper and had a quick look at it, one of the first things we could see is that we're in an area of faulted base Cretaceous unconformity. It's not uncommon. It happens northwestern Australia in and around Gorgon. The Tithonian unconformity is faulted. Got a stratigraphy that has been eroded. And then that eroded surface, the faults have reactivated again and generated another set of juxtapositions. And so really what you have to do, build an Allen map for the older section and then superimpose on top of that a second Allen map, which is faulted, eroded section. There's a number of papers out there that describe the geometry, and you can be in a situation where you've just got a straight unconformity, and then as you come more onto the slope, you get this faulted unconformity. So this is one of the issues we could immediately see in replicating the paper. So nonetheless, I thought, okay, well, it's worth having a go at it. And trying to build up Allen maps, ignoring the base Cretaceous and seeing if I could make sense of it. I took the top reservoir map and ran it into the software to start to build up the Allen maps and try and do the trap analysis. Now, one of the things it suggests is that this is a top reservoir map and that we've got, as you can see, the reservoir section on the right-hand side there, single reservoir from the heather right down to the top of the Dunlin group. When I started making up the Allen maps, the first thing I did was I went and checked how the wells tied to the map. And this is something I do every time I'm looking at a map. And went and got the well completion report and tried to see how I could get it to tie. And I started having problems at this stage trying to tie it. And then when I started building the Allen maps, given this one reservoir section, I wasn't able to make sense of the analysis for either juxtaposition by itself or SGR and juxtaposition. So I just really started to get confused about what was going on with the stratigraphy. And that's to a large extent. I started thinking, well, what am I doing wrong? Where am I in this? What am I not getting? And I guess it was talking then to Bill that we started thinking, well, is this something that you've dealt with in the past, Bill?
Titus basically inspired me to check and verify. So I'm kind of a data-centric kind of scientist, which means, given data, I'd like to use it, and that's particularly important in sort of geomechanics and some of the stuff that I've done before. So I read through the well completion reports carefully, and I also looked at the stratigraphic studies that we could find. I've always been fascinated by fluid pressure and particularly overpressure, so I was particularly keen on looking at the RFT and the MDT, the direct measurements of the pressure. Got the log data, which you can see on the screen right there. So, one thing that I'd like to do is get all the data together. I'll just flick ahead to the pressure data first. On the right, part B is the diagram from Yielding et al. It also appears in Fristat et al., both in 1997. And they didn't actually present a depth along the vertical axis there, my own plots. So that's shown on the far left, part A of the diagram. And Yeah, the foot wall is shown in purple, and the hanging wall is shown in light blue. So you can see there's a lot of complexity in this hanging wall part, and there's also there's the foot wall and the hanging wall. You know, they basically match the interpretation which is shown on the right. However, it does look like the situation, particularly in here, in the hanging wall, is a little bit more complicated. The other thing that I did is I plotted where there are unsuccessful tests. So when you're doing the MDT and the RFT data, you lots of times it doesn't work. So particularly in the hanging wall, there were a large number of unsuccessful tests, and they were well, they were scattered all around, but there's a lot of them up here. So this diagram shows an impression of a continuous gas gradient in here, but it doesn't really seem to hang together when we look in more detail at what's going on. Coming back to the first slide, what you can see, what I've done I've brought in, and this isn't in our discussion paper itself, on the far right, I've brought in the stratigraphic study, one of the three that we looked at in great detail. And that's a particularly interesting one because they did use all the core data. And it's important to realize that these wells were very well studied, lots of core data. So these guys used the core data and came up with this stratigraphic model, which has got note channels and mouth bars as well as shore face sands. So correlating then all these three together, we've referenced it to a radioactive shale, which is the purple horizon, shown straight across in all three of the studies. And the stratigraphic study is exactly the same as the hanging wall well number 14. So these the plots for the hanging wall, our plots for the hanging wall should match exactly with what's in the stratigraphic study. What you can see is that despite the fact that the 1997 paper said that this is one reservoir, it looks to be quite a heterogeneous story. So the stratigraphic guys are saying, you know, a mix of different types of facies and sands. And then when we look in detail at the resistivity data in particular, we've got the shallow resistivity, the deep resistivity, and the intermediate resistivity plotted here. So the shallow is in orange, the deep is in black, and the intermediate is in blue. So an area of good reservoir is going to show us a nice separation. So in the hanging wall, there is a good separation just above the radioactive shale. And you can see that corresponds with a spot where they did a drill stem test or a DST test. So there are two DST tests in there. Well 13, of course, was drilled first, and in that well they had a good reservoir looking interval in 3 spots. They did 3 DST tests, but then when they got around to well number 14, shortly thereafter, a year or two later, they obviously looked very closely for that top reservoir interval, but couldn't find it. So it seems that really the log data and what's going on in the well completion reports dovetail quite well and sort of confirm in our minds what the stratigraphic studies are saying, namely that these may be discontinuous sands. There's definitely the kind of behavior you would expect from a channel sands in a situation where things may not connect together very well occurring.
And I guess, Bill, one of the things that really came through with, the DSTs were in different locations. Well, that was driven a lot from what the RFT shows. And you've got there in purple for the 13, there's the dots for the RFT pressure measurements there. And then for 14, you've got the blue dots for the RFT measurements there. And you can see there's a set of the points, especially in the upper section, which Breton and Yielding have suggested is in the gas gap. These are all pressure measurements that were failed pressure measurements or overcharged. So was it of the 14, only one of them got a pressure out of that zone? And
yes, exactly, Titus. That's the top zone of the small blue dots. At about let's see, the depth is between 2950 and 3000. So we specifically mentioned that interval. 14 tests in there. 13 of them were tight tests. So it appears that they really did have a go at trying to find that same reservoir in well 14 that they found in well 13. And it just doesn't seem like it was there at all.
And so therefore, when they came through cased, because this is a case of casing, cementing, casing and cementing, and then perforating to do the test. These weren't barefoot tests. So, they decided that upper section of well 14 isn't reservoir section. And that has a really big impact on how we try and draw Allen maps then.
Yeah. So the other thing that we were able to then pin down very clearly is how to tie the map, or does the map tie? So you can see in the top of both of those sections, the gray is the Cretaceous. So the base of the Cretaceous is where the gray ends. And that's where supposedly the reservoir starts, according to the analysis presented in the 1997 papers. Well, it turns out that the level where the map crosses those two well paths is shown with the black asterisks and the black dotted line, and it's actually down from the top of the Viking group. And it turns out that some of the DST tests were above that level and some were below it. So, it's really hard to understand what was done and why. I suppose then we should just have another quick look at the pressure data. You can see in this case the foot walls in purple, the hanging walls in blue. It's that level between about 2950 and 3000, where we're saying that there's a lot of failed tests or tight tests in the RFT data. And there's only one point in blue at about 2985 constraining that gas gradient. So,
and it isn't that good a fit. And again, we could have a gas in here. We've got ourselves a deltaic environment. We've got a range of different little sand bodies. In theory, the targets are shore face sand, but in and around there, we're going to have distributary channels. So we could have some elements of gas out there in the well, but it's like it could be in a single channel sand.
Yeah, and then the other thing we did is we captured data from some of the other wells nearby, and they seem to follow a general water gradient. So it just highlights the fact that what we were a bit suspicious about is that, well, maybe these are very separate systems in different spots, different fluid columns with very different characteristics because they're isolated from one another.
And I guess that's what really came through when you plotted up that the black dots are the next terrace to the east. Is that right, Bill?
Yes, these
So
are generally over to the east. Yeah.
So that's a set of pressure points from further to the east of this, and you can see they're substantially overpressured compared to the hydrostatic line. So we've got a set of different pressure compartments in here. And again, whenever I'm seeing different pressure compartments, my first thing I think about is, hey, these are aquifers, and we're seeing coherent aquifer response, but they're separate, isolated, or confined aquifers. And this becomes really important when we're starting to look at the fault seal side of things, is that and think back of some of the work that the guys at Exxon have published shows that you can get a number of strange, or seemingly strange responses from having different aquifers through a system, and mistakenly put those down as fault seal.
So where does that leave us? Well, we set out to try to use the case study, and it didn't seem to work very well. So then we backed up a bit and said, well, what can we actually verify? What makes sense? And as Titus has explained, it's almost impossible to recreate good Allen maps from the data that we have. There are Allen maps in the 1997 papers, and the BCU, the Cretaceous, is not well documented. We couldn't figure out then really what's juxtaposed across the faults because of the problem with the position and the effect of the BCU not being very well shown. So then what do you do with the rest of it? The across fault pressure difference, we're wondering from looking at the pressure data how good the purported gas gradient in the hanging wall really is.
Because it's just based on one point, really, isn't it?
Yeah, yeah. And then if you wanted to do the V shale calculations, you could look at the log data and come up with something, but it's not clear from the paper how from the 1997 papers or the more recent paper what was done. So that leaves in considerable doubt the basic relationships, the crust fault pressure difference relationship to SGR, and how you come up with the right sort of calculations as is considered good practice.
And
So
I think so, Bill. Just thinking about that, the V shell calculation. If we were to go down that rabbit hole, we've got these two wells which are a considerable distance apart. We know that they're in different stratigraphic positions. We'd actually need to build up a stratigraphic model to say what we think the facies would be at the fault. The facies at the well are probably not representative of what's at the fault.
yeah, yeah,
It's an extensional growth system. The Brent deltas prograding out over these very shallow detaching systems, and we've got extensional growth faults, a bit like happening in Houston just now, generating accommodation space. The faults will cause changes in facies, and it's a non-trivial. This isn't a layer cake sheet sand system.
yeah. Bottom line for the whole thing is, what do we do? So you want to have a good concerted effort to try to figure out what's going on in the system. So there's a difference observed in the pressure between two wells, and when we sort of step back and say, well, what could be causing it? Um, some kind of fault seal is maybe one obvious choice, but maybe it's not the only thing. So we then considered, say, stratigraphic seal, and part of that's motivated by when we took a deeper look into the stratigraphy, we found these other new studies. And then when we looked at the log data that was public domain, we said, right, these studies seem to maybe be on the mark. The third possibility might be some kind of hydrodynamic effect or some other more complicated things that have been published before. And that's certainly a possibility. Based on our digging, however, we think that some kind of stratigraphic seal is the most likely. But by all means, if people think that it could be something else, by all means, have another look.
One of the things with that stratigraphic seal is that again comes back to the pressures, the consistent pressures we've got in the block to the east. You're sort of saying, well, how do we explain all of this data, not just the two wells? I think, and that's the beauty of having this so much open file data from Norwegian Petroleum Directorate.
And when you have it, let's use it. Let's figure out what's going on to the best we can. I suppose my perspective at this point is it's the most important thing to do is lay out all the possibilities and then work through them one by one and see what you can see what you can do. So if we said it a little bit more clearly, you should think hard about what the possibilities are.
So I think one of the things in particular is, as you say, is lay out all those possibilities and start to have a look at the lowest energy solution. But then, Bill, you've read up quite a bit of the work that Claire Bond's been doing on bias. What do you think are the different forms of bias that we could be introducing when we do an analysis?
Okay, so we figure what we need to do. The way to work in these uncertain situations, which fault seal commonly is, we often, we wish we knew exactly what was going on, but many times there just isn't enough data. So we reckon what you need to do then is think about all the possibilities and avoid important biases. So chief among those, we'd mention the key types of bias are say what Claire Bond and colleagues have termed availability bias. So that's where we already have a theory or an explanation that everyone knows and everybody accepts. So let's just use that and get on with it and don't worry about other possibilities. So, do we rush too many times to say fault seal is the answer? Second one would be confirmation bias. So in that case, we see what we want to see, we hear what we want to hear. So we got to watch out that, when we try to figure out what the possibilities are, that we look carefully at what information is coming to us. What can we see? What can we tell? And then another one is anchoring bias. So This is one where we focus on an explanation or a mechanism in particular because it's proposed by a famous researcher or someone that is particularly well known. So we figure they must be right. So anyway, we come up with a list of our possibilities. So mentioned before that the possibilities in this case might be fault seal. We've sort of turned up the possibility of stratigraphic seal. So every hydrocarbon trap has to have some form of lateral seal. In this case, maybe it's stratigraphic. And then the other ones, you could say hydrodynamic. What are the best words for that, Titus? Seals that are explanations that you could have where you've got multiple things going on.
That extra set of pressure points out to the east really does tell us something about how these aquifers are connected.
Right. Okay.
And that and that when we're thinking about the bias, the fact is we do have these pressure regimes that line up in a north-south sense. And it's not just Breton's work, but also some of the work the fault analysis group have put out there show these pressure regimes that are north-south consistent. And I can imagine them with a shore face sand of the Tarbet shore face sand. As the sea level's going up and down, that shore face is moving in and out, moving off onto different fault blocks. And that gives us lateral connectivity that will mean that we'll have the same sorts of aquifer gradient north-south. But then as we start to move east-west, we've got separate sand bodies. And, depending on the amount of burial, they will have different amounts of overpressure.
Yeah. So it's a complicated story. Yeah. All right.
Well, I don't know if it's complicated or it's uncertain. Because one of the things that's interesting about this is that we have got some consistent pressures in there. And, it's tempting to say, well, hey, it's complicated. Well, it can't be that complicated to have those pressures so consistent. It's just we're uncertain. We don't have the data. And unfortunately, we don't have the seismic. We've only got the well data. But there's only so much we can see with that.
Yeah, and I suppose that in a sense is what we've come down to, is we've said, all right, well, what's the easiest explanation, or what are the alternative explanations? And stratigraphic seal is, of course, one of them. In fact, I think it's the one that, based on our digging and looking through all the data, we think that some kind of stratigraphic lateral seal is the most likely explanation in this case.
And because if we go to the non-miscible pressure ideas that Peter Vorlik and the guys from Exxon have put forward, they are complex models where you've got different aquifers being separated by non-miscible phase. And so we get ourselves down to, well, could be fault seal, could be stratigraphic, it could be this non-miscible phase. Well, good old William of Ockham with his razor, you sit there and say, well, what's the simplest solution? What's the lowest energy solution? Which is the one that gives us the least complexity or the easiest story?
So where does this leave us? Well, we're a little bit worried about the data situation. We'd love to see more data somehow get into the public domain so that it's possible for somebody to propose a particular mechanism or model, or say, this is what we think is going on, but then for others to go and have a look at the same data sets and work through the same problem and verify what they've said, and maybe come up with alternative explanations. So we'd love to put a call out there for data to be made public to the greatest degree possible. And we think this is particularly important when we get around to contemplating other problems that are much more regulated than the oil and gas industry. For example, we've got CO2 sequestration coming up. It's a very, very important topic. We've got toxic waste storage. We've got nuclear waste repositories, and we've got groundwater problems all over the place. So as we enter these other areas and try to take these things we've discovered about fault seal from the oil and gas patch, how do we know that they're going to be workable in these other areas if we can't go through and verify them? So
I guess one of the things that's interesting when you say that word verify, is it verify, or the call is, to a certain extent, can people put out enough data when they're putting putting papers together to allow other workers to invalidate. And I think the guys at Preprint and the guys at Bad Lease should be commended for putting so much stuff out there. You know, we progress these ideas not by proving they work, but by disproving them, and that's how that's the basis of the scientific method. Yeah, and if we're going to take this stuff into CO2, what do you think, Bill? Is that a fair call, or?
Yeah, I'd say it certainly is, and you hate to be overly negative, but in many cases, good scientific progress comes about by, as you say, disproving things, and that may seem negative at times, but the truth is probably the most important thing, and arriving there as best you can is really that you're really winning when you can take all the data you've got, lay out all the possibilities, and try to figure out what you can really say and what you can't, and then report it responsibly. And that's a problem that all of us will face when we get into these other more regulated, more contentious, and certainly more political issues.
And I guess maybe that's a difference. There's a lot of people in the oil industry just now, oil and gas industry, who've lost their jobs. There's a big pivot to a range of different other industries. And I don't want this to sound trite, but if you're putting up a prospect to be drilled in the deep water Gulf of Mexico, and it isn't successful because you don't find oil, well, that's between you and the shareholders. But if we're looking at disposing of CO2 or rad waste, and it's going through a legislative environment, that's different. We just have to be more careful about what we say and what we claim.
Exactly. Yeah.
It's a different bet.
Mm-hmm. Just remember that showing a mechanism, and a mechanism is just a mechanism. There could be lots of mechanisms operating. It's sometimes quite complex, but just showing that a mechanism is plausible is not good enough. If you want to say, want to go out and say this mechanism controlled the hydrocarbon contacts or controlled the fluid flow, well, that's quite difficult to do, actually. And so showing it's plausible isn't good enough. If you're going to make a statement like this is what happens, this is what controls, then you do have to subject yourself to a little bit higher standard.
And I guess the other thing with that is thinking about that higher standard. Is it a conservative mechanism we're putting forward or an optimistic mechanism? And that comes back, I guess, to the Gulf of Mexico, prospect example. We can afford to be optimistic in the oil industry because we might lose some shareholders' money, but the upside is that, we're going to find a whole lot of oil. When we start thinking about some of these other areas, we really do have to be properly conservative. And remember that whenever we introduce a membrane seal mechanism, it's over and above the base geometry juxtaposition. So, when we're proposing science, when we're using structural geology in these more regulated areas, how can we be conservative about what we say rather than overly optimistic?
Right. Yeah. Yeah. No, it's not easy.
Hi folks, I'm out for my run, sunny Mittagong. Having finished editing this talk, I hope you enjoyed the talk. Since we put the talk together, the paper has been published in JOLSOC, along with the reply of the other authors. So head in there, download it, have a look. If you're having problems getting hold of it, please get in contact with us. The next talk that Bill and I will be doing, similar to this one, where we're going to go through and deal with some of the comments, and we'll look at some of the papers that we suggested that we go through and reference. So there's more interesting stuff to come out of work looking at pressures and faults in the North Sea. Hope you enjoy it. We'll see you soon.